Okay, the fundamental theorem of algebra. I had to restart the video, but and I already wrote these in. But here's what it says. It says the degree of a polynomial function is the same as the number of zeros or solutions. So, for example, a seventh degree polynomial function would have 7 zeros or 7 solutions. Okay, and if it has the 13th degree, then it would have 13 zeros. Okay. All right, conjugate pairs. So I've got a bunch of complex numbers here. These are all written as complex numbers. Complex numbers have what's called a conjugate. So a conjugate, all you do is change the sign of the radical part. And remember, I is the square root of -1. So the conjugate of a plus bi is a minus bi. Okay? The conjugate of 3 plus 2i is 3 minus 2i. And it's true this doesn't have a real part, but I could write it as 0 plus 7i. So the conjugate of that is just -7i. Okay, works in the same kind of way with radicals when I don't have I. So a minus b root x would be the conjugate. And here the radical part is negative, but I just changed the sign. So these two are a conjugate pair, and then those two are a conjugate pair. Okay? So any zeros involving I or a radical are going to come in conjugate pairs. Okay. So that means if 3 root 7 is a solution, I should have said is a solution, or is a zero. If 3 root 7 is a zero, then so is -3 root 7. Okay? And it kind of makes sense if you think about the quadratic formula or completing the square. The part with the radical, you always have the plus minus in front of it, whether you're using quadratic formula or whether you're taking the square root of both sides of an equation. So that's why those come in conjugate pairs. Okay? All right. So next problem here. First, I'm looking at this and I'm thinking, how many turning points do I have? And I've got 2 of them, right? 2 places where the curve turns around. And that means that this is going to be a 3rd degree equation. Okay? So if this is 3rd degree, well, using the fundamental theorem of algebra, then I know the number of total zeros that it's going to have. It's going to have 3, right? A 3rd degree function should have 3 zeros. Okay? Now, the real zeros are going to be the x-intercepts. Okay, so just looking at the graph, hey, there's only one real zero right there. So that means there's one of those. Okay, but wait a second, we said there's 3 total zeros. Well, the other 2 are going to be imaginary. Since only one of them is a real x-intercept, the other 2 are going to be imaginary. And those imaginary ones should always come in conjugate pairs. They're going to come in pairs. So it makes sense that there would be 2 of them. There's never going to be one imaginary 0 or 3 or 5 or 7. There's always, they come in pairs, so it's always going to be an even number. Or you could have 0 imaginaries, but there we go. Okay? All right, so next up, I'm going to write the simplest possible polynomial equation in standard form for a function with these zeros. Got some typos in here. Okay, so I've got these zeros, but I know the imaginary ones are going to come in conjugate pairs. So there's a hidden 0 that I have to realize, okay, if 3i is a 0, so is -3i. It has to work like that. Okay, so you got to recognize that there's the conjugate. If there was a radical in there, that would be the same kind of deal. Okay, so now what I'm going to do is I'm going to think about the zero product property. Well, what if I had this set equal to 0 and I had it all factored? Okay, if -2 is a root, then x plus 2 would be one of the factors, right? Because if x plus 2 equals 0, then x equals -2. Okay, if x minus 3i is one of my factors, that would give me a 0 of 3i if I solve this for x, right? And likewise, I'm going to have this. Okay, so I'm kind of thinking about the factored form of this. Okay, and then since this says an equation, I don't want to leave it set equal to 0. You could write f of x if you wanted to write it in function notation, but I just put it as y. And now this is not in standard form, so I have to multiply it all together to put it in standard form. Some people are just going to start multiplying from left to right. You can do that, but I wouldn't recommend it. It's going to be a big mess like that. It will work out if you do it correctly, but it's going to be much easier if you first multiply the conjugates together. Okay? And the reason why, when I'm multiplying conjugates together, if you look at the outer and inner, they're going to be opposites. So they're just going to drop out, and it's going to be a lot easier to work with. Okay? So I'm going to leave the x plus 2 alone for now, and I'm thinking first, outer, inner, last. First, x times x. Outer would be x times 3i. Inner would be negative 3i times x. And last is negative 3i times positive 3i. So negative 3 times positive 3 is negative 9, and I times I is I squared. Okay? Now, if you don't really need the outer and the inner because they're opposites. So if anytime you're multiplying conjugates, you can kind of just skip that step if you realize what you're doing. Okay? All right. Now, I got to be careful here because I squared, remember that's square root of negative 1 times itself. So I squared is negative 1. Okay? So I've got the x plus 2 here, and then I've got x squared. This is negative 9 times negative 1, so that would be positive 9. Okay? So now I got it down to that pretty quickly. I don't have to worry about any more i's, and I do one more round of foiling, and I'll have my solution. So first would be x to the third. Outer would be 9x, but I'm actually going to do the inner first because that's higher degree, just so that's already in standard form. So I'm doing first, inner, outer, and last. Okay, and then there's no like terms to combine there. This is in standard form, and there we go. Okay. Okay, on the next page, we're going to try one that involves a radical 0. Okay, so let's see. Okay, so write the simplest possible polynomial equation with these roots. So we got negative 3, positive root 2, but those always come in conjugate pairs. So I'm supposed to realize, oh, there's another hidden root that they're not telling me about. But I know if positive root 2 is a root, so is negative root 2. Okay, so I'm going to set this up thinking of how this would look factored. I'm just going to put the y in from the beginning, but one of my factors would be x plus 3 to give me the x minus 3, right? And one of my factors would be x minus root 2. That would give me this 0, right? And one of my factors is x plus root 2. Okay, so then I have to multiply this all together to simplify this. And again, I would recommend multiplying the conjugate pairs together first. It's just going to make my life much easier. You could multiply those two, but it will be a big mess, trust me. Okay, so, all right, first would be x squared, right? Outer is going to be x root 2. Inner is going to be negative x root 2. And last, and I find this is the part that gives people the most problems. I've got a negative times a positive. It will come out negative, right? Root 2 times root 2 would be root 4. And hey, root 4 is just 2, right? So I can simplify that part to 2, so I'm going to have negative 2 at the end there, okay? Not only that, but my outer and inner terms are opposites, so those just drop out and make life a lot easier. So then I've got it down to x plus 3 times x squared minus, and this would be minus 2, right? And then I just have to FOIL once more, and I can be on my way. So first would be x to the third. I'm going to do inner before outer because inner is going to be a higher degree, so that would be 3x squared. Outer would be negative 2x. And last would be negative 6. And there we go. Okay. All right, so let's talk about irrational and rational numbers. So irrational numbers do not repeat or terminate. In decimal form, I'm talking about. The decimal goes on forever. So the most famous one is pi, right? You've seen those long lists of pi. It goes on forever without repeating. But actually, all irrational numbers will do that. So anytime you've got a square root of something that's not a perfect square, like the square root of 2, nothing times itself equals 2, if you put that in a calculator, it spits out a long decimal, but it actually keeps going on forever. Your calculator will only display so many decimals. But there's no pattern happening there either. There's no repeatable pattern, and it doesn't repeat, it doesn't terminate. There should really be a ... if our calculator was smart enough to say that. Okay. So anything that involves a square root that's not a perfect square, or pi, is going to be irrational. Okay, so like 7 pi is also irrational, or 3 root 2, for example. Okay. All right, so rational numbers, then these do repeat or terminate in decimal form. Okay, and technically it's anything you can write as a ratio of integers, as a fraction. So let's take 1/3, for example. 1/3. Okay, so I get this long decimal, 0.333. That goes on forever. So yeah, it never terminates, but it does repeat. It's just 3's, right? Repeating. So that counts as a rational number. Okay. All right. So a rational number, that leads us to the rational root theorem. Okay. So there's a little formula to get the possible rational roots. The possible rational roots are going to be given by it's going to be a fraction where you've got the factors of the constant. This is supposed to be a division bar here. So I'm going to take the factors of the constant on top. That's my phone there, whoops. Okay, so I've got the factors of the constant, and I'm just going to use a lowercase p to symbolize that. And that's going to be over the factors of the leading coefficient. And we're going to use a q for this. I guess it doesn't matter if it's uppercase or lowercase. But anyways, we often use p and q for that, okay? So on this example, and this is just going to give me a list of possible rational roots, okay? So roots, by the way, are just the x values that give you a y value of 0. So if this was equal to 0, it would be solving for x, okay? So this graph is going to be the x-intercepts, really, the roots, okay? So this gives you the x-intercept, possible x-intercepts that are rational, okay? So in this case, the constant is the piece with the constant term is the one without an x value, so it's just a number. So in this case, p equals 6, okay? And then my leading coefficient here is 5. That's that's the coefficient of the highest degree term. So in standard form, it'll always be up front. So q is going to be 5. Okay? So when I'm thinking about the possible rational roots here, I'm going to take the factors of p, well, the factors of 6 then. So I'm thinking, what goes into 6 evenly? What integers? So I know 1 goes into 6. So does, I'm going to space these out a little bit, and I'll tell you why in a second. So does 2, so does 3, so does 6. All of those things go into 6, but actually the negative versions of those go in as well. That's why I left a little space, because negative 1 goes into 6, so does negative 2, negative 3, and so forth. I didn't do a great job spacing that out there, but the positive and negative integers that go into 6, okay? So for 5, only thing that goes into 5 are, only integers are 1 and 5, okay? So you could actually list all of these out one by one, all of these possibilities, like, you know, -3 over +5, -3/5 is one of the possibilities. And I like to just list them as a big fraction like that with the plus or minus in front of each factor. But you could make a big long list of all of the combos there. Okay, so those are my possible rational roots. Okay, so looking at this next one, my possible rational roots here, I'm going to take the factors of 6. So those are all the things that go, all the integers that go into 6. Okay, and then I'm going to put that over the factors of 8. So 1, 2, 4, and 8 are all the factors. Okay, and that's going to give me a list of all the possibilities. Okay, so let's put this to use in a bigger context here. Okay, so here I've got this polynomial equation. First, I'm going to list the possible rational roots. You know, you could try factoring this by grouping, but it's going to be a dead end. Okay, and you know, we had problems before where they just gave us a one of the zeros, and then we can one of the factors, and you can start dividing it out to whittle it down. But sometimes that's not given, and then so we're going to have to use the rational root theorem to get things started. Okay, so I'm going to list the possible rational roots. These are the things that x could equal to make y equals 0. So these are my possible rational x-intercepts, in other words. Okay, so I'm taking the factors of -8, which are the same as the factors of +8. Okay, over the factors of 1. So really, think about those. Any of these, if you divide by positive or -1, it's just going to be those integers. So my possible rational roots are going to be positive and negative, 1, 2, 4, and 8. Okay. All right. So those aren't necessarily all going to be roots. They're not all going to be x-intercepts, but those are the only possible rational ones. Okay. So if there are any rational ones, they're there in that list. Okay. So what we could do, there's really 8 options, positive, -1, positive, -2, and so forth, right? So we could start just trying to divide by, you know, x plus 1, divide by x minus 1, until we get a 0 remainder. And once we hit a 0 remainder, we know that we found a rational root, okay? And that's what, you know, that's what our grandparents did. And we could do that. It might take 8 rounds of synthetic division or long division to find one. But let's use some technology to make this, to make some educated guesses. Okay. So what I'm going to do is graph this function on a graphing calculator. You could use Desmos if you don't have a graphing calculator. So I get x to the third plus 3x squared minus 6x minus 8. Okay, and I'll hit graph, and I can see I have a weird zoom going on here. Oh, I can see the function a little bit, but just since the x and y axes look thick, I'm going to go to my standard zoom. That's going, it's kind of a 10 directions in each way. So I hit the zoom button up there, choosing zoom standard. So hopefully I can see a little better what's going on. Okay. So now I got some good candidates here. It looks like it crosses, I'm kind of looking at the x-intercepts. This looks like it crosses at -4, -1, and +2. All of those would be on this list. So here's my guesses. I don't know for sure if these are x-intercepts, because this could cross, you know, instead of at -4, it could be -0.401. Maybe it's an irrational root there, okay? And that could happen with any of those. But I know in this list, those are the only ones worth trying. I can see for sure it does not cross at +4, right? So I'm not going to try that one. So these are the ones that I'm going to try out, okay? So I'm thinking, okay, if remember, that means if x equals -4, that means one of the factors would be x plus 4, right? So if I was dividing this equation by x plus 4, I'd put -4. So you put the root itself in the not the opposite, right? But the opposite when you've got the factor. Okay. Then I'm looking at my terms up here, and you could do long division, but I much prefer synthetic division when I can use it. And I'm just going to see if I get a zero remainder here. And there's no missing terms there. Always be looking for that, right? So I'm pulling down the 1. Negative 4 times 1 is negative 4. 3 plus negative 4 would be negative 1. Negative 4 times negative 1 is positive 4. Negative 6 plus 4 is negative 2. Negative 4 times negative 2 is positive 8. Yep, I got a zero remainder. Okay. So I could go ahead and try the rest of these. If you wanted to try negative 1 and 2, you could try the whittled down version and keep whittling this down. So that's one way you could handle this. Also, I can think, well, what have I done? I've taken this and I've factored out x plus 4. And what do I have left? Well, I have this polynomial, right? So this is the remainder. This is a constant. This would be negative 1x and x squared. Okay, so I could keep doing synthetic division, but also I've got this down to a place where if it's factorable, I can just factor it by hand, right? So I can take that quadratic trinomial. So anytime you get down to 3 numbers here, you got it to a place where you should definitely be able to factor it if it's factorable. And it's not necessarily factorable, but sometimes it will be. Okay, so I got a negative 1 up there, negative 2. So I'm thinking, how can I multiply to get negative 2? Well, what about 1 times negative 2? So that will add up to negative 1. So it factors like this, and that means my possible rational roots. If this was equal to 0, what x could equal? X could equal negative 4, x could equal negative 1, and x could equal positive 2. Those were my guesses, so they all turned out to be good guesses on that one. Okay, let's try another on the next page. Got this one, and I got my steps here, so we're going to find the possible rational roots, and then we'll factor those out. Okay, once we factor that out, we'll do all the factoring we can, and if there's any parts that you can't factor, you could always use completing the square or the quadratic formula. So this says complete any remaining factoring. This actually should say solving of any remaining parts with the quadratic formula. Okay, so looking at this, yeah, we wouldn't have any way to factor this by hand, but let's find the possible rational roots. Okay, so my possible rational roots I'm going to get from the factors of 20 or negative 20. Okay, so I'm thinking, what goes into 20? 1 does, 2 does, 4 does, 5 does, 10 does, and 20 itself does. There's a lot of them there. Okay, factors of 1, just positive or negative 1. So I'm really looking for these integers, 1, 2, 4, 5, 10, 20, or the negative versions of those. Okay, now I definitely don't want to test all of those out with synthetic division. So to make things a little quicker, I'm going to use a graphing calculator or Desmos or something like that, some sort of graphing utility to get a look at this. Okay, so let me type this in. This is going to be, hopefully you can, oh, you can see that there. Okay, x to the 4th minus 4x to the 3rd plus x squared plus 16x minus 20. Okay, and then I'll graph it and take a look. Okay, so it looked like it crossed at negative 2 and also at positive 2. And that might be a triple root there. Who knows? Okay, so, but let's get our guesses down. So x could potentially equal negative 2. Not sure because it might be a decimal that's just really close to negative 2. And it looks like positive 2 might work as well. Okay. This scale only goes out to 10, so I'm also checking for 20, which is off screen. So I probably want to zoom out a little bit to see if there's any more roots that I can see. And I don't think so. We can zoom out again, but I don't think it's crossing the x-axis anywhere else but besides those places. Okay, so let's, oh, sorry, my guesses were off screen. There they are. There's my guesses. So these are going to be the ones that I'm going to try out with synthetic division. So let's see. I'm checking -2, which would mean, x plus 2 would be a factor. Not missing any terms here. So I just take these coefficients, and I want to see if I get a zero remainder. If I don't, that's okay. I'll just move on to one of my other guesses. Okay, or I'll double check my work too. It's another option. Okay, so multiplying -2 times 1, adding this, multiplying -2 times -6 is 12. 1 plus 12 is 13. Multiplying -2 times 13 is -26. Adding that together, multiplying one more time, and hey, look at that. Got a winner. Okay, so now I'm thinking, where am I at? I factored out x plus 2, which means x would equal -2. -2 would be a rational root. Okay, and what I have left here, this would be -10. This would be 13x, -6x squared. This is x to the third. Okay, and looking at that, you could, anytime you've got it down to a place where you can factor, you could go ahead and do that. But I don't think I can factor this even by grouping. It's not going to work out. So I'm going to check out +2. Okay, now you could check +2 in the original to see if it's a factor. But I might as well try it in this one, because it should go into this if it goes into that original equation, and then that'll help me break this one down further. So I'm going to try the +2 out in this one to break it down further. Okay, and I'll see if I get a zero remainder here or not. And yes, I did. Okay, so I already had factored out the x plus 2 up here. Now I've factored out x minus 2 as a factor, right? And then this is what's left, right? That'd be x squared minus 4x plus 5. Okay, and now I was kind of suspecting that this might be a double root or even a triple root. But now I can just look at this and say, wait a sec, I should be able to factor this on my own. And if I can't factor it, I could use quadratic formula or complete the square. So I'm thinking with that, with a diamond problem, you need two numbers that add to -4, same two numbers multiply to 5. And so let me see, 1 times 5 or -1 times -5. Nope, that's a dead end. Okay, so I'm going to have to go to one of my other options. So know I've got -2 there. I know I've got +2 here. And then if I set all of this equal to 0, zoom out, I'm almost off screen. If this is all equal to 0, and I know it's not factorable, my two options I got left are complete the square or quadratic formula. Either one's fine. I'm going to complete the square. I like to complete the square when my b is an even number and my a is 1. Okay, so let's see. I am going to move the 5 to the other side. It's not the mystery number that's going to give me a perfect square trinomial, so I subtracted that 5 to move it to the other side. And I'm going to be adding the same thing to both sides so that I can get a perfect square trinomial. Okay, so to get that mystery number, I'm using b over 2 squared. Okay, the b was -4. My mystery number is 4. So I got that on both sides. Okay, now I should be able to factor this, and it should be something times itself. And again, you could set up a diamond problem if you like, but it's going to be x minus 2 times itself, also known as x minus 2, the quantity x minus 2 squared. Okay, then I've got a -1 over there. Okay, let's take the square root of both sides. Okay. I want to solve this for x, so I'm going to add 2 to both sides. I'm going to slip the 2 in front of the plus or minus. And then the square root of -1 is I, right? So I don't want to leave a negative under a radical because I can write that with I. So hey, look at that. So I did get 4 solutions. This is a 4th degree, so it should have 4 solutions. 1, 2, 3, 4, right? 2 of them were imaginary, so I only had these ones you won't be able to see on the graph because they're imaginary. So these ones are the only ones that are actual x-intercepts, but I still got my other zeros right there. Okay, and that is it for today.